Today's lecture is going to be technical. So we will also review a lot of stuff from study 52. Hopefully, you still remember it, okay? But of course, I need to start from bivariate normal distribution. So, and I believe this is what is to be expected, yeah? So bivariate normal distribution and the corresponding (2D) random vector. Okay? Because we often talk about random variables and their distributions as synonyms. A point which I keep stressing out is that these are really different things. Okay? We might have different random variables which possess the same probability distribution. But here I also emphasize 2D random vector because we now study vectors. Okay? So it makes our life even more exciting. Okay, but now, so bivariate normal distribution for now is a 5-parameter class of positive functions on R squared. Okay? We do not discuss the probabilistic meaning of these parameters. Not yet. So, and f of xy is defined as 1 over 2 pi times sigma 1 times sigma 2 times the root of 1 minus rho squared times the exponent of negative 1 over 2 times 1 minus rho squared times x minus mu1 over sigma 1 squared plus y minus mu2 over sigma 2 squared minus 2 times rho times x minus mu1 times y minus mu2 over sigma 1 times sigma 2. So I close the square bracket and I close the figure bracket. So let me double check. So this is here. Okay. So here x, y is an arbitrary point on the plane. And we have 5 parameters, which are mu1, mu2, and mu1 and mu2 are arbitrary real numbers. Sigma 1 and sigma 2 are arbitrary positive numbers. R1 plus is the set of all positive numbers. And finally, parameter rho, so it's Greek letter rho, takes on the values from negative to positive 1, where negative and positive 1 are not included. Okay. And let me give you some references where you can find it. So Evans and Rosenthal, it's example 279, but the absolute value of rho should be less than 1. There is a typo in the book. It's less than or equal to 1. Okay? We cannot have positive or negative 1 here because the denominator will blow up. We don't want that. Okay? So it's just a typo. And in Ro's book, so now for Ro's book, do you see when I write here? Aliyah. So it's seen, yeah? Okay. And okay. The furniture doesn't block it from you, I hope, but you're welcome to stand if it's necessary. So by Ro's, actually, I mean a first course in probability by Ro's. Okay, so it's example 6.5d. Okay, and this is also discussed in the book by Gnedenko, and I'm going to comment on it in the due course, because Gnedenko gives detailed intuitive proofs. Okay? So, but first of all, are you comfortable with this definition? So I spoke with Professor Damoris on Monday, who was course coordinator last fall for STAR-B 52. So he, of course, told what STAR-B 52 students saw last fall, and it's not one of the most favorite topics for students. So it's calculus of several variables is employed, but you did see it last fall. Okay? So therefore, it makes my life a bit easier because it's not something that is completely new for you. But first of all, a point I want to make is that when you see mu1 and sigma 1, you immediately think these are the mean and variance. Okay? That's going to be true, but do not speed up, please, because it's to be proved. For now, I just introduce the 5-parameter class of positive functions. Is it clear? So I have the right to consider such positive functions on R squared. Okay? And then I just say I want to consider the cases where mu1 and mu2 are arbitrary real numbers. sigma 1 and sigma 2 are arbitrary positive real numbers, and rho is between negative and positive 1. And of course, the endpoints of this interval are to be excluded. So it's OK. It's not probability theory yet. It's still calculus of two variables. Are you with me? And then I need to prove a few things, of course. First of all, I'm to prove that for each set of parameters specified when they take on admissible values of these parameters. So by admissible values, I mean the values from the parameter domain which is specified on chalkboard. OK? So I choose such numbers. And then what else do I need to prove in order to justify that it is a legitimate joint probability density function? So one property is obvious. So it is a positive function. Like it may be somewhere non-negative, but clearly it's positive for any value x, y on the plane. What else do I need to check?
Integral over R2 is 1.
Yeah, very good. The integral over the whole plane is 1. Yeah, that's the only other thing which is to be checked. Okay. So it's a claim from calculus that double integral over r squared f of x, y. So you can write dx, dy. Of course, you can write dA if you want. So technically speaking, you need to write dA if it's integral over r squared, but dx, dy is permitted. OK? Like, so we need to show that it's equal to 1 identically. You know it's not number 3. It's identity, yeah? For all admissible values of 5 parameters. And this happens to be true, but it requires some effort. OK? So we need to make changes of variables and so on. Then Jacobians sounds like a very exciting stuff, yeah? So we need to use various transformations, etc., do cleaning, and at the end we get such a beautiful result, which I fell in love with when I actually learned this stuff in calculus course. So therefore, we are OK, and we got a legitimate joint PDF, and so it's a joint PDF of a certain 2D random vector, capital X, capital Y. OK? Next. So you, of course, are expected to know the marginals. So next, find the marginal PDFs f1 of x1 or f1 of x, which is just